In the previous segment, we discussed about the reason or the motivation why we need to transform the stresses, and then to be specific, we discussed about the plane stress condition because the 3D general 3D state of stress is a complex thing to analyze. So, we restricted ourselves to the case of plane stress, where only sigma x, sigma y and tau xy are the stresses which are present. And then we were talking about why is it so important to transform these stresses to other orientations, so that we will have a complete picture of the state of the stress at a particular point and not be fooled about the values which we have got by applying the strain gauge rosettes at a given direction. Okay. So, to do that, let us say we have this okay, I will draw it here. This is our square on which and then I will define my x coordinate like this and the y coordinate like this. Okay. And then I am interested in evaluating the stresses as seen by these primed coordinate system, which are rotated by an angle, say theta, with respect to the original. Okay. And it is exactly same as thinking about that you have rotated the elemental, the infinitesimal square on which you are actually trying to see the stresses. Okay. And to show the stresses, let me okay, what I would do is from in the original direction or in the original axis, there was sigma x, this was sigma y, and it was tau xy and it was tau yx. Okay. I am not drawing on this side, you know what exactly the same thing. Okay. For the last time I will be drawing otherwise. So, this is sigma x, this is sigma y, and this is tau yx, this is tau xy. Okay. And this is about the point P. And now you can think of this rotated coordinate system, or you can think of a particular what I will do is say, which color should I take? Yeah. So, that means you can otherwise think that no, this will be bad color, maybe white. Yeah. So, now your the elemental square you can think of like this also. Okay. Where sigma x dash and sigma y dash will be acting. So, I will remove this, I will undo this thing here because it is becoming very clumsy here. So, instead of that, what I will do is I will draw it in a different picture, where again the same coordinates I will show, like so this is x, this is y, and this is x prime and this is y prime. And now instead of in this orientation of the elemental square, what I will do is I will draw it in this way. Okay. So, this is my elemental square on which now stresses I will show again. So, this will be sigma x primed, this will be sigma y primed, and this will be tau xy, this will be tau yx. So, tau yx, sorry, primed, right? So, these are primed, and tau xy, and similarly here it's sigma x primed, this is sigma y primed. Okay, so this is the element in the rotated position, and this is the element in the original position. Okay. Now, so to relate the values of sigma x, so what we are set to do is this sigma x, sigma y, and tau xy, we want to transform them to, or we want to see the relationship, how they get transformed into sigma x primed, sigma y primed, tau x prime, y prime. So, this transformation rule that we are looking for. Okay. And for that, what we will do is, we will pick, a segment like this of from this elemental square. Okay, and that thing I'll draw separately here so that things will be clearer in a bigger picture. Let me draw that here. So, okay, so that's that segment which I had drawn here. So, here that white segment is what I have drawn here separately. Assume that this area is, say, delta A. Okay, and okay, now that means this area will be delta A cosine of theta. Okay, because this angle makes theta with this. Okay, and this area is delta A sine of theta. Okay, now our coordinate systems are in this way. So, this is my x primed, this is my y primed, and I think the color has been shifted, does not matter. This is x and this is y, and we are trying to evaluate this is sigma x primed delta A is the force that acts, because if this area is delta A, so the force which is acting in this direction, because see, we will correlate them by using the force balance. Okay, so that is the basis. So that is why we are writing everything now in terms of forces, not in stresses, and that is why we introduce the area element, so that once we multiply them with the stresses, we will get the forces. Okay, and this side, let me first write all the normal stresses. So in this side, it will be sigma x prime, because see, this plane is perpendicular to x, the original x. So the normal stress here will be sigma x times delta A cosine of theta, delta A cosine of theta, and similarly this one, okay, sorry, this one will be sigma y, because see this plane is in the direction perpendicular, or this plane is perpendicular to y direction. So, sigma y acts on that times delta A sine of theta. Okay, so these are the normal stresses, and coming to the shear stresses. So, let me draw here. So, this is our tau x primed y primed delta A, and here so this way is my tau xy, again xy, they are not primed, times delta A cosine of theta, and similarly in this direction tau yx. By the way, they are same, right? Tau yx equal to tau xy delta A sine of theta. So, these are all the forces which we have now drawn on this small element. Now, let us write the equation of equilibrium. For that I will need some space. So, let me try to shift this whole thing to here. As far as possible, I have shifted it. Let me see if I am getting space. Now, let us say we write the equation of equilibrium in the direction of x prime. Okay. So, then what you will get is, so this is suppose the positive direction. So, I am writing sigma x primed delta A. This is bad. So, x primed delta A is in this direction, then the component of this in negative x direction is minus sigma x delta A cosine of theta, but it is in this side. So, this is theta. So, it is cosine theta component, cosine of theta. What else is there? Say first let us consider the normal stresses. So, this one is 90 minus theta. Okay. So, you will have minus sigma y delta A sine theta and its sine theta component. Then let us come to the shear stress parts. So, this one will have its sine theta component. So, minus tau xy delta A cosine theta sine theta. Similarly, here it is cosine theta. Okay. So, minus tau yx sine theta and cosine theta. So, these are, I think, yeah, this is done, this is done, 4. Okay. So, all are done in x direction, x dash, x prime direction. So, this has to be 0. So, that is the equilibrium equation in the x primed direction, and in the same way you can write the equilibrium of force in the y prime direction. I will just write it down for you. So, this is like the summation of all the forces in y prime equal to 0. So, that is the equation which we wrote here, and similarly if we write summation of all the forces in y primed to be 0. So, what you will get is so tau x primed y primed delta A. So, that is this, okay, and everything in this form. Now, here it is plus sigma x delta A cosine theta and the sine theta. Okay, then here it's minus sigma y delta A sine theta cosine theta, then minus this tau xy delta A cosine theta and its cosine theta, and similarly one more, I think this yeah, so this one will have a component, right? So this one will be plus, yep, so plus tau yx sine theta and its sine theta component 0. So these are the two equations which you require to figure out the relationship, and along with this you just use the identities of trigonometry of cosine 2 theta, sine 2 theta and all those things, and you will come up with these beautiful expressions after simplification, which I will just write down. You can fill in those details, they are not very complex. They'll come something like this: sigma x primed will be equal to sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine of 2 theta, then plus tau xy sine of 2 theta. Okay. So this is the relation. See, on this right hand side everything is in the in terms of x and y coordinate system, and this side is the x primed coordinate system, and similarly the tau x primed y primed you can get like this: minus of sigma x minus sigma y over 2 sine of 2 theta plus tau xy cosine of 2 theta. And in fact the other term, which is the sigma y primed, you can directly get by replacing theta with theta plus pi by 2. Okay. So if you do that, you will get this expression as sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 times cosine of 2 theta, okay, minus tau xy sine of 2 theta. Okay. So just observe a point which is important. If you just add them, okay, so these terms will just cancel out. I'll just put some brackets over here so that it will be clear to observe. Okay. So then, so they will just cancel out, and it will become the relationship will come out to be x primed plus sigma y primed is equal to sigma x plus sigma y, and this is not an incidental thing. It's a very well known fact, which is this is called one of the, if you go back, you know, the stress tensor here, where is it? I think the beginning, yeah. So here the trace of a tensor, so if you just add the diagonal terms, it is an invariant. They call it an invariant. The trace of this matrix is an invariant under the transformation which we are talking about. When you rotate the coordinate system, so the trace of that matrix doesn't change. Okay, so that's a very general property of a tensor, and this is what we are observing here. Okay, so but now this is what we were looking for till now. Okay, so that means now you see this. So these are my values in primed coordinate, and everything on the right hand side is in the unprimed coordinate. Okay, so that is what we were trying to figure out, right? So if you see here, the unprimed coordinate values in terms of the the primed coordinate values in terms of the unprimed coordinate values. So that's what we have derived now. So once we have derived this, obviously you can write a code and we can put things and then you can always get these values, but there are certain other tools, techniques and methods which are worth discussing. So we will come back to them and we will discuss them in the next segment. See you in the next segment.